Hi everyone, today we're going to take a look at part alignment in Fusion 360. We have made these support beams and sent them out for anodizing. Now they need some engraving on the top surface. I have 3D printed a set of soft jaws to hold the part in the correct orientation along its axis, but unfortunately the location in the other directions is not going to be accurate enough for our small 0.1mm depth of cut on the engraving pass. We're going to use the top surface here as our Z datum, this hole as our X and Y, and then from here we will use our part alignment to improve this location on the machine. The same principles apply if you're trying to balance stock on a forging, casting or 3D printed part, or perhaps trying to align a complex part back on our milling machine for further work, like a mould or die tool for repair or modification. To traditionally align this part, I would have to take a series of measurements across the top and keep adjusting the part until it sits correctly. Varying in the skill of the machinist, this can take a considerable amount of time. Now we have to take measurements across the face of the part and keep adjusting my C-axis until the part is aligned along the X-axis. As you can see, this is a lengthy process and there's lots of room for error. So now we're going to take a look at how we can automate this inside of Fusion 360. Here we have the part assembled into our soft jaws. Let's make a part alignment from the probing tab. We have three main fitting types, 3, 4 and 5 axis. 3 axis will let the part translate across all three of the orthogonal axes. 4 axis will not only do the translation in the 3 axes, but also allows you to select one additional rotational axis. And 5 axis will allow us to rotate about 2 axes and get a full alignment. Now remember, even if you have a 5 axis machine, you can still select 3 axis if that's what you want on your part. Let's place some inspection points on our part. We're going to try and have a good spread across the component and restrict the 6 degrees of freedom. So I'm going to try and choose points with a good distribution across the surface. Imagine you had a square block of material. You wouldn't want all the points on the top. You'd want them spread across all the faces to give a good fit on the alignment. To make things run a bit smoother and more efficient, let's drop the approach down and over travel to 3mm. Because all of this is for our trace toolpath that has a depth of cut at 0.1, I'm going to tighten up my tolerances. And finally, just lower that retract height. We now need to post-process the inspection toolpath for alignment. This creates an NC program, so just change the settings here as you normally would for creating NC code. Now we have our NC code, let's go over to our machine and run the program. We're now executing our probing program on the machine, and we will retrieve the results file once that's finished. So we have our results file from the controller and now ready to import them back into Fusion. Notice the red cross on the part alignment folder is now a green tick. This shows that the part alignment has been calculated correctly. Wow, those results look good, but don't be fooled, they were not that good before the alignment. We can take a deeper look into the alignment and see what it's had to do. At the top here, we can see how much the alignment has to shift the part, both in linear translation and axial rotation. This graph shows the individual points mapped so the position along its x-axis represents the deviation before the alignment, and the position along the y-axis shows the deviation after the alignment. So, for our results, we can see that at the two extremes of the x-axis, we have negative 0.136 and positive 0.247. After the alignment along the y-axis, we have the extremes of negative 0.017 and positive 0.015. That's quite a big improvement. I like to think of a bounding box around these points. The wider the rectangle, the worse the points were, and the shorter the rectangle, the better the alignment has worked. If you see a square, then we have a problem. This means that the points were just as bad after the alignment than before. There is another way to see this result, the same as the normal inspect surface table, but here we have an additional checkbox where we can flip the points before and after the alignment to see a comparison. Now that we are happy with the alignment, we can post out all the toolpaths in this setup with the alignment applied. Again, set up your NC program as you normally would, and before we hit OK, look at the operations table. Here we only have the trace operation selected, as Fusion knows we do not need to run the inspection path again. Having a look at our NC code, you can see our 3-axis toolpath is now a 3+2 toolpath. So what's happened is Fusion has had a look at the transformation required and adjusted our toolpath to suit. Again, over to the machine and let's run the NC code. You may be thinking that was a huge C movement and our part can't be that far out, but what you are seeing is the result of 3 axes in CAD being transformed onto the 2 axes the machine has. So a tiny movement in B results in a large movement about C and A. We have now fully engraved our part nice and evenly across the surface. With part alignment, you can have the confidence your toolpath will be in the correct place every time.